Hello children, welcome to channel Sube. Children, I am going to discuss today question number 33 from the MCQ part of 2021 Physics New Syllabus paper. Three long straight conducting wires A, B and C. A, B and C are kept at the three vertices of a square as shown in the figure. So this one is the square. So at three vertices they have kept these wires. They are parallel to each other and carry equal currents of I directed out of the plane of the paper. The direction of the resultant magnetic flux density at point D is given by point D. Here the flux density is what they want us to find out. So there is no wires here, only the point is there. So children, I think you can understand this problem. That means there are three wires like this, which are parallel to each other like this. There are three wires like this, parallel, and the wires like this, coming out that point like this, like this. So there are three wires. So when we look at this system from above the plane, this A, B, C, D, that is how we can see it. So at the bottom there might be a house like this. If I draw like this, you can visualize the 3D picture. That is why I draw it. So like this, the three wires are like this, parallel to each other. So the current is coming out of the paper. So here is a dot, therefore not a cross. Currents are coming out of the paper. So let us try to solve this problem. Only the direction they want. So let us take a copy first of all. First children, let us try this one, this wire A. The current is I, the current is coming out of the paper. So let us place our right hand. We have a right hand here like this. So let us place the thumb overlapping this current I like this, directed to the out of the paper, because they have said the current is coming out of the paper. So the small fingers are directed to this way. So therefore at this point D, the flux density must be this way towards D to C like this. Therefore let us mark it. So the flux density must be like this. So let us use blue color for this, and also this dot let us mark as blue. So the direction is to this way now, like this. So the distance is x. Now let us try this one, this wire C. So let us place our right hand thumb on the wire C, so that it is thumb is directed to the direction of the current. Current is coming out of the paper, so the thumb also now directed to out of the paper. So at point D, the small fingers are directed to this way, away from D. So like this. So we have to therefore mark the direction of magnetic flux density like this away. So the length of the arrow must be equal with this blue one, because the current cycle, distances are equal. Therefore this magnetic flux densities must be also equal. Therefore the arrow must be equal in length. And also you must notice that this angle theta also equals, these two angles are equals, because this one is a right angle, so we took first from here and the second one from here. So therefore these angles are 45 degrees. Now let us go to this wire. Now children, let us try this one. This wire, the current is coming out of the paper, the wire is B. So let us place our hand to find out the direction of capital B, flux density. So let us place our thumb here overlapping wire B, so the small fingers are directed downwards vertically. So then it must be like this, the direction of B, magnetic flux density. So it should be shorter than these arrows, because why? Because the distance you can see is larger, this distance is larger than this x. X is smaller, this one is larger. So therefore when the distance is increased, so the flux density decreases. So therefore we have to draw a shorter arrow like this. These arrows are equal because distances are equal. Now children, let us get the resultant of these three capital B's, that means the magnetic flux densities. So we have to turn this one to this way, so we get the component like this. So this angle theta is 45 degrees, and also this angle also same, theta 45 degrees. So you have to turn this capital B value also to this way. So same, because magnitudes are equal and also the angles are equal. So therefore like this we get the component like this. So the final resultant B value, the flux density, magnetic flux density, is downwards vertically. So we have to add it with this one, with this green one. So let us add it like this. So finally we get this one is the resultant magnetic flux density. This one is the final one. So you see it is downwards, because this angle cycle, this magnitude cycle. Therefore the resultant of these two, red and blue one, is to downwards, and already this one green one is already downwards. So the final B is downwards. So therefore the answer must be downwards. Downwards means to the direction they have previously shown. This direction, simple A, this one is the answer then. So let us select the first one as the answer. So let us check question number 33. The answer is first one. So that is the way you have to solve this problem. Now children, we have selected the answer. So let us do something else now, because this one is a past paper. You will not get this paper again. When you sit for the exam, you will get something else, but familiar with this type of question. They might ask the magnitude of final magnetic flux density. Therefore, let us try to find out. That is not difficult. Therefore, as a target question, let us try to find out the magnitude of, now we have already find out the direction. So let us try to find out the magnitude, because next time they might ask that question in your exam. So you must have learned the magnitude of flux density is given by mu naught I divided by 2 phi r from these types of parallel wire. So in the lesson you learn not like this. In the lesson you learn like this. You draw a wire like this, and the direction of the current like this, and you mark it like this, I. So the distance you take like this, and dash line, and you mark here the flux density like this as a cross. So this is the lesson normally you learn. So I am going to recall it, because this diagram is something complicated. So this is the lesson you learn in the classroom, perpendicular direction. So you take this length as distance as r. So the current you know, then you mark magnetic flux density here, capital B. So B equals, directly you are taught the equation is mu naught I divided by 2 phi r. So this is the equation. So you don't have to derive it, therefore your teachers don't derive it and show you how this come. Just they give this equation to keep in your mind. So since these wires are infinitely long, like this, you mark dash lines also. So this is the lesson you learn in the classroom. So the only difference is this wire is horizontal. In this question they have given vertical wires like this. So you have to turn this diagram like this. This diagram you have to turn 90 degrees like this. So like this you have to turn it 90 degrees so that the wire is vertical. So the equation is this one. You don't have to derive it, you have to keep in your mind. By heart you should be able to write it, this equation. So let us use it to find out the magnitude of this final magnetic flux density. So since the current is I, here also I, the distance you have to change. What is the distance? So this one. So I am taking this red one. No, so we are using this red one first of all. So the distance is this one. Distance is this one, perpendicular distance to the magnetic flux density. So the distance is given as x. So you have to write x here. That's all. Others are same. Current is I, mu naught 2 phi, they are constant. So x you have to write like this. So let us now write the equation for blue color magnetic flux density. The same, because the distance is same. So the distance for blue color I have already marked, this one, x. So you have to write B equals mu naught, the current is I also, same, 2 phi, again x, distance is x. So you have to add, you have to get the cos theta, no, cos theta, because you have to turn this to this way, take the component is cos theta of this one, cos 45, that is to downwards to this direction. Initially without cos theta the direction is to this way. So this one parallel to this way, but we have to take the component, vertical component downwards like this. So that is why we write this cos theta, cos 45. Here also the original direction of magnetic flux density is to this way. So here this equation gives the magnetic flux density to this way, the magnitude to this way, but what we want is to downwards. So therefore we have to get the cos theta value. So here when we write it to downwards, the cos theta comes here, cos 45. So the final one of both these magnetic flux densities, let us take this green one later. First of all, let us find out this red one and blue one. So here without this green one, without this green one, these two, how to find out? We have to add this one and this one, just because this blue one is to downwards and also red one is to downwards, so we have to add. So the final B of this red and blue, I write like this, red and blue, what is the value? Mu naught. So we have to, we can multiply by 2, because all the terms, all the variables and constants are equal. So therefore 2 times mu naught I divide by 2 phi x. Cos theta is 1 over root 2. 1 over root 2. So now we can write the magnetic flux densities of red one and blue one like this, 2 times mu naught I divided by 2 phi x root 2. So now let us take the green one, this one we have to add now to this one, to this term. So this B, green B. So that also the equation is this one. So let us write that mu naught, the current is same I, 2 phi r. What is r? R is so this one, this the magnetic flux density we are talking about. So distance is this one, So how to find out it? Using this diagram. So this angle is 45 degrees. So this length is x. So you have to turn it this way. Then what is this one? X cos 45. But we want this total length. So 2 times, this one also the same. So the final total length is 2 times x. Cos 45 means 1 over root 2. Then root 2 we can write here instead of 2. What? Root 2, then 1 root 2 cancel. So root 2 x, we get root 2 x as the distance. So let us write it here. Instead of this r, we have to write root 2 times x. Now let us simplify. Now all these are to downwards. This one also, red and green, red and blue, magnetic field densities are, the flux densities are simplified like this, and we are going to add it to the green one. So finally we get the final density, flux density. So 2 phi root 2 x, both denominators are equal, therefore let us take 2 phi root 2 x. You don't cancel this one, don't cancel, then they will not be equal, therefore you will have problems now then. So let us now write just the numerators, 2 times mu naught I plus mu naught I. So now we get 3 times mu naught I divided by 2 phi x root 2. So furthermore we can't simplify. So this is the final magnitude of magnetic field density, resultant magnetic field flux density, field density or flux density, both words are used. So this is the final value. So you have to practice this and be ready, because next time when you are sitting you might get a question of this type. They might do a little change like that to this same problem. So you can't say then the question is difficult, because they say then this one is a past paper, we have changed only a little bit, so then you have no answer. So therefore children, practice this, you might get this type of a question. So I have done now a target question 2 for you. So I think you are happy. So you have to make me happy also by subscribing my channel. Don't subscribe twice. If you have already subscribed, don't subscribe again. If you haven't subscribed, then only you have to subscribe my channel. So thank you very much for watching my videos. See you tomorrow at 6 o'clock. Goodbye.